quickly recapitulate what we have seen yesterday. So, yesterday we started off with concept of what is called a sequential circuit, right? The sequential circuit, how are it different from the one which we have seen earlier? Because the circuits which we have seen so far were the combinational circuit. That means the output were dependent on only the current inputs. Now we are going to see the circuits in which the output is dependent not only on the current inputs but also on the previous behavior of the circuits. So such kind of circuits are called sequential circuits, isn't it? So we have introduced the concept of sequential circuits. We have also seen that the sequential circuits are formed out of the combinational circuits and a memory element, right? So we have introduced a memory element. We have seen that simply by giving a feedback of two inverters won't do the job, just because we fail to give input to that design. So we came up with a NOR based or gate based memory element, right? So let me revise that. So NOR memory element. So how was it? Let me first draw that. So there were two those NOR gates which we have connected in such a fashion that there will be two inputs here, right? And we have made some cross connections here, isn't it? So the connections were somewhat like this. So the construction was something like this. So this we named it as S R. This is let me name this as QA new. Okay, so N indicates new and QP new. So where S and R are the inputs, QN, QAN and QBN are the current or new outputs, right? And let or new states, you can say. Let QA and QB be the previous states. When we draw the characteristic table, now the behavior of this, what is called as NOR based memory element depends on how we give those inputs, right? And on the previous values of or the previous states of the outputs. So let's draw this characteristic table. Yesterday we didn't note down the things properly, so let's do that today. This is S, this is R, it will be QN, QAN and QBN. So when S and R are both 0, 0, see what happens here? When S and R are both 0, 0. Now this is OR, NOR gate, right? So let me draw the truth table for that. 1, 0, 1, 1. Now here I am assuming the ideal condition, okay? Assuming that gate delays are the same and its ideal situation there is no gate delay and so on. So I am assuming that this is, let it be two inputs A, B, and this is B A or with B Now this is NOR gate. What is the truth table for this? It is 1, then rest of them is 0. What if both of them are 0? Okay, when we are feeding S and R are 0, okay, what happens? No, at least one input. Okay, so I didn't connect it properly. So, sorry, pardon me. I should connect it. Should connect like this, right? It's a feedback. Yeah. So when both of these are 0, 0, see what happens carefully. One input to this NOR gate is always 0, right? One input to the NOR gate is always 0. Consider this one. One input to the NOR gate is always 0. What we expect at the output, whatever is the previous one, it will be the complement of what is there at this terminal. That means, what was the previous state here? Previous state was QB here. It will be complement of that. That will be QB ka bar. Okay, and I mean the states will remain unchanged, right? So I will write it like no change. If QA is not equal to QB. See what I am saying? Now see here. Let me mark this. Okay, see here. When both inputs are 0, 0, what happens? Even if it is 1, it is 1, 0 or 0, 1. Okay, assume that it is, it is 1, 0 or 0, 1. Output, what is there? Output is always a complement of that. Assume that there, that at this terminal there is a 1. Okay, output will be 0 here, and that it will be 0, 1 here. Let me write that also. Okay, assume that it is 0. Okay, here. So output will be 1 here, and this 1 will be traveled, and output will be 0 here. I mean the state will remain unchanged. There will be no change if these are different. Okay, assume that there is a 1 here. Assume that there is a 1 here. This 1 will be complemented as 0, and that 1 will also reflect here. So again these states will be unchanged if QA and QB are different. Okay, are you getting? But assume that if QA and QB are the same. Assume that, are you getting this? I mean, and when they are different, that means they are 0 or 1, there won't be any change. I mean, the states will be retained. Assume that both of them is 1, 1 or 0, 0. See what happens. Let me drop this. QA is not equal to QB. If QA is equals to QB, that means let it be 0 or 1. Consider any case. Let it be, the previous inputs, let it be 1, 1. See what happens? 0, 1, 0, 1. What is the output? Both at 0, 0, right? Both of them will travel here again. What is the output? 0, 0, 1, 1. Again, both of the 1 will travel here, and then what is the output? 0, 0, and so on. See what is happening when both of these inputs or the previous states are equal. What happens? It keeps shuttling, it keeps oscillating, isn't it? So this is an undesired situation. Okay, we should always avoid this situation. So it will be oscillations or this undetermined stage, so indeterminate you can say. They won't. What do you mean by indeterminate? There won't be any stable state there. Okay, so here it's stable. Are you getting the things? Stable. Yesterday we didn't note it down specifically. Today we are doing that. Indeterminate. We can't determine. Indeterminate. If QA and QB. What are QA and QB? The previous wala output. So this is unstable situation. We should always avoid that. Is it okay? Now let's erase this. Let's consider next state, next case. consider the case where, you know, S, no, this is for 0 0, right? Consider the case for 0 1 when S and R is 0 1, right? So S is 0 here, R is 1 here. See here, when, you know, now consider the simplest case. When either of the input is always 1, what happens? You tell me. Output is, you know, we guarantee output is guaranteed to be 0, no matter what the previous state is. So here it is guaranteed to be 0. Even though, you know, it may not be, it will, you know, settle down to 0. Okay, the fluctuations will be such that at the end you will get the stable 0. You can try it out. Okay, you can try it out. And this 0 0 0, it will be again 1 here. Okay. Is there any future, you know, further changes which are happening? Are there any further changes which are happening? 1 will be traveled here, 0 will be here. So 1 1 will again be 0 and 0 0 will again be 1. And this is the stable state, isn't it? So when it is 0 1, you will always get at the output, and means QA as 0, QB as 1. Is that okay? So the output will be 0 and 1 always. So, getting really bad. See, this kind of, you know, the way I am treating this, you know, topic, the same treatment may not be available in the book. So, you know, I mean, the way of explanation may be different, but, you know, this is the subtle point which you need to capture. They will simply specify the characteristic table, but, you know, the understanding and the words and the subtle point between that you have to capture. That is actually left uncovered, or, you know, left unnoticed by the readers. So that's why I am emphasizing these facts. Okay, so this is the stable output. Should I write it stable here? So it doesn't matter what the QA and QB are. This is going to be the case always. Is going to be always the case, and that is what is the stable, you know, the stable output, right? Stable, right? Stable. Let's consider the case, the another case where, see the situation where, you know, this S is 1, R is 0. Now let me erase this. Are you understanding the things now? Are you getting the things? Yeah. Let's consider the case where this S is 1 and R is 0. Same thing would happen, but in the reverse fashion, right? The output, you know, this will be 1 always, and this will be 0 always. Yeah. Should I write that? 1 and 0 always, and that will be a stable situation. Yeah. Stable in the sense, will there be any further changes? No, that means stable situation. There won't be any kind of fluctuation or oscillations, which is otherwise the case when, you know, this condition is there, 0 0 and equal inputs. Let's consider the case 1 1. You tell me what is the output. Now I am considering the case 1 1. Doesn't matter what the inputs are, 1 will always get the output as 0. So it is again stable. See, many books again I am saying, they won't specify, you know, explicitly like that. They will specify it as undetermined form, and no, this is undesired form, and then they will write the description that when you change the inputs from 1 1 to 0 0, and then how, that is how they describe. But we should be very clear that the stable output will be 1 1. That is always the case. That is the stable. So we are, you know, we want always the stable conditions. Okay, we that the unstable conditions are always, yes please. Oh, sorry. Yeah, is that okay? Is it no? Which case? Last case, okay. Okay, it doesn't matter. Okay, you take the case where QA and QB are different, you are saying, or equal. No, see, unstable, when I am saying unstable, that means the output is keeping shuttling. I mean, once it keeps changing. Stable in the sense, it's like, it won't change anymore. It won't change anymore. So, here it was changing. Like, I'll give you an example of stable and unstable. See here, let S and R be 0, 0 always. Okay, let us fix that. Okay, S and R as always 0, 0. We have seen that. Okay. This is the main case. Okay, when S and R is always 0, 0. Okay, when one of the input is always 0, 0, the output is, the complemented form of the input, right? The complemented of the form of the input. Okay, but when these two inputs are different, then only that is the case. Assume that both of these inputs are the same. Let it be 1, 1. What happens? 0, 1. When it is 0, 1, it will be 0 here. 0, 1, it will be 0 here. Again, they will travel back here. 0, 0, it will be 1 there. 0, 0, it will be 1 there, and so on. The output is keeping shuttling, right? I mean, output is not stable. That is what I am calling it as an unstable state, and undesired or undetermined form, right? So we don't want that. See, we should always, we should not forget our purpose. Our purpose was to build a memory, a 1-bit memory cell or a memory element, isn't it? We were happy with that, we were not happy with the simple cascade of 2 NOT gates, right? Just because we were not able to feed the input, we were not able to change the data. That's why we went for the cascade of 2 gates, NOR gates, right? And we found that if we make these cross connections, we can easily save a data bit, okay, only if the inputs, if it is 0, 1 or 1, 0. I mean, there are some stable situations, there are some unstable situations. Let's keep, or let's capture the things which we want. Let's retain the things which we want. Let's skip the things which we don't want. Okay, let's try to make it more stable and more nice. This memory element, right? So is this okay? What I'm saying? This is okay, all of you. Now, why I started off with NOR gate? Just because it's a universal gate and all. So if it is possible with the NOR gate, it should also always be possible with the NAND gate and all, right? So can you please try it out? Just replace this with NAND gate, and can you prepare the characteristic? No, you should not say truth table. Now it's a characteristic table. Okay, so prepare a NAND based memory cell. But when I wrote the statement after that, yes, so that thing is actually now those we have written in words. So these things are getting captured in this table now. Okay, here the input is, now see here, when it is 1, 1, initially it is 0, 0, but as soon as we change to the inputs to 0, 0, it will keep shifting. That is what I have written in words, right? Initially it will be 0, 0, but as soon as I change the inputs to 0, 0, okay, when assume that initially we have given 1, 1, output is 0, 0, stable. As soon as I change the input from 1, 1 to 0, 0, the outputs will keep shuttling. That is what we don't want, and that is what we have written in the words. But those words are getting well captured in this characteristic table. Okay. Now there is no need to specify it in words, right? Now these things are very well captured in this table. Isn't it? That statement was like undetermined state if the inputs are changing. I have written the statement, right? The input, if we change from 1, 1 to 0, 0, then is only that case is going to happen, isn't it? So that is how the books specify. That is how the books usually specify. Yeah, is it okay? Let's go ahead. Here I am assuming that everything is ideal, no delays and everything. So let me tell you this. इस बार का गेट का पेपर EC का, मैं EC का हूँ तो EC का दूंगा, कंप्यूटर का नहीं पता. एनालॉग और डिजिटल का 10-10 मार्क्स का पूछा था, 10-12 मार्क्स का पूछा था, दोनों सब्जेक्ट्स. ओके, दैट मीन्स पास होने के लिए ओपन के लिए कट ऑफ चाहिए 25 मार्क. ठीक है, तो मतलब अगर आप 10-10 मार्क का 20 मार्क तो वैसे हो गए, और गलती से नेटवर्क का पिछले बार का याद होगा तो 2 मार्क तो इजीली मिल जाएंगे. मतलब इजीली आप पास हो सकते हो गेट एग्जामिनेशन. एंड गेट क्वेश्चंस वर रियली नाइस. MOS के हमने जो पढ़ा है MOSFET, no, I'm again saying you are fortunate enough to learn all these MOSFET, transistors, BJTs, hybrid models, digital circuits in your first year. You are lucky to have have that understanding of those subjects, because otherwise other students will learn those things in the third year or second year. What I'm saying is based on only 1 year, okay, इसके बाद आप एलिजिबल नहीं हो, आप बच्चे हो. क्यों? क्योंकि एलिजिबिलिटी आपको गेट एग्जाम के लिए थर्ड ईयर तो भी अपियर चाहिए, मतलब थर्ड ईयर पास तो भी चाहिए, फाइनल ईयर अपियरिंग तो भी चाहिए. उसमें भी वो प्रिंसिपल का लेटर लेके जाना पड़ता है कि भाई हाँ मैं सच में मतलब बच्चा नहीं हूँ, मैं एग्जाम दे सकता हूँ. एंड बट व्हाट आई एम सेइंग इज इवन आफ्टर फर्स्ट ईयर ऑफ द एग्जाम यू कैन वेरी वेल क्रैक द एग्जाम इजी. सो योर एम शुड बी ऑलवेज टू स्कोर अबव 800 और 900 गेट स्कोर. मतलब 1000 में से गेट स्कोर इज डिफरेंट, गेट मार्क्स इज डिफरेंट. गेट स्कोर जो है 800 1000 की 800 900 के ऊपर आना चाहिए. बेस्ट टू हैव 1000. AR1 वाले का 1000 रहता है, सो उसके रिलेटेड सब रैंकिंग रहती है. व्हाट आई एम सेइंग इज वी हैव लर्नड ओनली 2 इलेक्ट्रॉनिक्स रिलेटेड सब्जेक्ट. इफ यू आर कंप्यूटर साइंस स्टूडेंट्स, doesn't matter you are eligible or not, if you go for EC gate examination, you'll easily crack the gate exam. So what I'm saying is, these questions in the gate examination, this kind of questions were also asked. I mean, there were some differences, there were some modifications, like gate के delays उन्होंने दे दिया 10 nanoseconds 20 nanoseconds. अब ढूंढते बैठो कितना delay रहेगा क्या. There were some I've tried to introduce some of the questions in the exam, but I will also try to introduce in the further examinations. I don't guarantee which examinations it would be, but the hint is that you should practice as much as possible. Okay, all जितने भी competitive exams के I mean in the library किसी और की books available नहीं होंगी पर अपनी ज़रूर होगी. I've also procured जो गेट की एग्जामिनेशन या फिर IAS के जो बुक्स रहते हैं मल्टीपल चॉइस क्वेश्चंस के प्रैक्टिस एग्जाम्स के, उसके भी बुक्स हैं. यू टेक दोज बुक्स, प्रैक्टिस एज मच एज पॉसिबल. ऑनलाइन भी बहुत सारा मटेरियल अवेलेबल है. You do that. Okay, मैं ये बोलना चाहता हूँ कि जो हमने पढ़ा है वो यूज़ होता है और उससे बहुत फ़ायदा होने वाला है. ठीक है, तो बेटर टू कॉन्सेंट्रेट. NAND बेस्ड मेमोरी एलिमेंट, I'm taking very slowly here. Simply replace the NOR with the NAND. Make the same connections, the crisscross fashion. So SRQAN QB. Now you tell me. Now this, let me write the truth table for this NAND gate. So it's 0001 1011. This A B AB Rabba. NAND gate बोलो यहाँ पे 0. Alright, let's prepare the characteristic table for this. Let this be SRQAN QB and consider the case 00. Tell me, when it is 00, okay, it will always be 1. Is it a stable situation? Is it stable situation? Try to give some more, try 2 to 3 more times. Okay, you will get a stable output as 1 1 always. So should I write 1 1 always, 1 always? So I mean yeah, it is always the case, right? Always in the sense, it doesn't matter what the previous things are. I mean QA and QB were 0 1. You tell me. You take the situation. Let's consider the situation as is 0 and 1. When one of the input is 0, it's guaranteed to be 1 here. Okay, you assume that it's not 1. I mean there'll be some input here. You'll always get 1 here. Okay, if one of the input is 0, you'll always guaranteed to be 1 here. If it is 1 here, then it will be 1 1 0. Is that okay? Is that a stable situation? Is that a stable situation? Yes. So right here, what should it be? 0, right? 0 1 stable always, and yeah, stable. So I'll write always and stable here. So that is also stable situation. This is also stable situation. is also stable. Again, I am saying the treatment in the books is slightly different than what I am saying. Okay, so yeah, let's consider the case 1 0 1 0. Again, the situation will be the same, but in the reverse fashion. So should I write it directly? Yeah, so I'll write it directly that it will be 1 0. Is it a stable situation? Yes. See what happens, it is 1 1. Let's consider this case 1 1. When it is 1 1, see here, when it is 1 1, the output is always a complement of the another input, right? Isn't it? So it depends on, see, if it is 1 here, it will be 0 there, and if it's 0, it will be 1. But I may take 0 here, and then it will be 1 here, and you know that 1 will affect as that 0 here, right? So you know, if the input, the another input is different, that means QA and QB are different, those states will be retained, right? There will be no change if QA and QB are different, right? So let me write that. So it will be no change. I've written no change earlier. That was the case for 0 0 and QA and QB were different, right? There no change when bolo when QA not equal to no, this is a stable situation. This is a stable situation. It won't change. There won't be any change. Change means stable. There won't be any change means there will be stable. No change in the sense, you know, the QAN will be equal to QA, QB will be QBN will be equal to QB, right? QBN will be equal to Q. Is that okay? I mean, new states will be retained as it is. Example, see here. When it is 1 1, see here. Okay, confuse mat hona. Dekho yahan pe. What I am saying is, assume the case when Q and QB are different, opposite. I mean 1 or 0. So let us assume, you know, this will be 1 and that will be 0. Okay. Now 1 1. You tell me 1 1. It's 0 here. That's 0 1 0. Will they be retained? Yes. So earlier, what was QB 1? What was QB earlier? QA earlier 0. Those states are retained. Yes, so no change, the states will be retained, that's a stable situation. But when Q and QB are different. So let me write it stable here. Let's consider the case when Q and QB are the same. Now similar thing arise, you know, similar difficulty arise as we were getting. Yeah, let it be. Let's consider the case when both of them are 0 0. What is the output? 1 0. 1. These will travel. Is that a stable situation? They will travel back. 1 1. Now tell me the output. 1 1. And they keep shuttling. They keep oscillating from between 1 0 0 1. So that's not a stable situation, right? So that will happen when 1 1 is the input SR and Q and QB are the same. Okay. Let me write that. So oscillations or unstable or indeterminate state, indeterminate oscillations that is unstable. Unstable in the sense the output doesn't remain constant. When, tell me, QA, and we should always avoid this situation. Why? See, our aim was, what was our purpose? Our purpose was to create a memory cell. Okay, it should retain a bit information. See here, is that purpose served? See here, in the previous case also, this assume that usually the S is the input. Okay, usually the S is the input. Now whatever the S is, that is getting retained at the at the Q terminal. Okay, always, and that is a stable situation. Forget about this situations. Forget about this situation. Okay. Come here, same case is applied there. Okay, that 0 will be, okay, let me see. Yeah, see here, the case when this 0 1 0 1 is retained, right? You forget about the other cases because we are no more interested in those cases. See,
अगर मैं 0 देता हूँ तो 1 हो जाता है, तो वी डोंट वांट दैट, वी वांट ओनली द whatever we give that should be retained. Okay, that purpose is not solved in this case and that case. That is purpose solved only in between, when the inputs are the complement, and that is what we expect also. A memory, what we expect, a variable which I am storing it in a memory element, that should be available in complemented and uncomplemented form. That's it. Okay, so that we don't require any kind of extra NOT gate, just because for implementation or realization of any logics or any design we require both of them, right? We may require both of them. Alright, so is this okay? Understood? Well, fine. Now, see, now we have simply created a memory 1-bit memory cell. Okay, somewhat we were able, we didn't successfully have done our job, but somehow we have started off. It may sometime happen that, okay, I may wish that at my control it should be retaining the bit. So there should be a controlled input. So if I wish to have a controlled memory element, I can have that something like this. So this is what is called as controlled or enabled or controlled memory element. Controlled or enabled. Or gated, you can say. What is gated also? Using only NAND gates, and now onwards will be constantly on NAND based implementation. NOR base is also possible. And just for an example, we are going to take that NAND based implementation. This is, let me write it as enable. SR. Please see the changes which I am doing. Okay, S I have written it above. Okay, otherwise there will be complemented. So there is a purpose for that. QAN, QBN. Can you write a characteristic table for this? Now there are 3 inputs, right? I mean there is an enable. See what happens. Now let's prepare the characteristic table first. So the enable pin and the S, R, QA and QBN. Alright. So let's consider the case when the enable pin is 0. Okay. Enable pin is 0. So let it be 0. Let me write the NAND table just because for convenience. 0 1 1 0 1 1. So let this be A B bar. So this is 1110. Yeah. So when one input is guaranteed to be 0, the output of this will be always 1. Is that okay? This will be 1. If one input is always 1, the output is guaranteed to be in the complement of that. So the state will be retained. Okay, I mean if it is 0 1, 0 will be complement of that, will be, I mean the state will be retained. Is that okay? So there will be no change when the QA and QB are different. When QA and QB are different, isn't it? When enable is 0 and this SR doesn't matter what they are, they really doesn't matter, right? The SNR doesn't matter. QA and QB will be no change, right? There won't be any change, no change. When? Bolo. QA not equals to, but what if they are equal? What if they are equal? Let it be 1 1 or 0 0. Indeterminate form again. Is that okay? Same case will arise. So indeterminate form or oscillations when QA is not is equals to QB. We don't need that situation, just because see, when feeding only we require only one input. Okay, we have taken as two inputs, but we'll see that for data how we can convert this to one input and so on. Is that okay? Now that is done. Let enable pin be 1. You tell me now. Okay, now let me rub this. When this enable pin is 1, see this is the case. When the enable, if 1 is the input, okay, always the 1, then the output will be complement of that, right? What should I write it here? S bar, here R bar, right? That is the same. Let us select S and R. Let's say it is 0001 1011, right? So 00 01 1011. Can you tell me the output when they are 00? When 00, it will be 11 here. When it is 11, what was the situation then? When it is 11, okay, this is equals to 1 here, this is equals to 1, okay. Again the same situation happens, okay, when they are equal, okay, when they are equal, indeterminate state, and when, let me rub this first. Are you getting the things? Yeah. When it is 00, two situations may change. So there won't be no change. There will be no change when QA is not equals to QB, and there will be indeterminate form when QA is equals to QB. Is that okay? Correct? आप भी 1 1 लेके देखो, 1 1 का 0 हो जाएगा, and those 0 will travel back, and 1 0 का 1 0 0 1 का फिर से 1 1 हो जाएगा, and that will oscillate, keep on oscillating. Let's take another situation when enable is 1 0 1. Now the things become pretty easy. You tell me now. Enable input is always 1. Let me write it. Yeah. S is 0, R is 1. S is 0, मतलब यहाँ पे 1 हो गया, यहाँ पे 0 हो गया. बोलो आउटपुट में क्या आएगा? Now one of the input is always 0, output is always 1 here. 1 will travel, and that 1 1 will always be 0 here. So output, whenever S is 0, output, QA is always 0, always. Is that the case? So it is 0. So no, that is a stable situation. That's a stable situation, isn't it? That's a that is a stable 0 and 1, and that is a stable. Yeah, the stable situation. Can you complete this? Complete this. 1 0 के लिए बोलो क्या आएगा? Stable. Calculate for 1, all 1. You tell me. Tell me for all 1. One. Is that okay? Is that a stable situation? Stable. Now this is the characteristic table for this circuit element. So this is a characteristic table I should write. So avoid the name truth table. Okay. So characteristic table. Now I will give a name to this. Okay, this S and R is called this complete, this whatever we have built so far is called as a latch. It's called as a latch. Let me name that truth table for a latch. Or this is also called as SR latch. So this is called as SR latch, just because this S indicates a set, R indicates reset. See the thing. When S is 1, see here, when S is 1, it will set. When S is 0, it will reset, and so on. I mean, when reset is 1, otherwise it will be reset. That it will be resetted in that sense. Okay, so S and R is called a set reset latch. Latch मतलब वो दरवाजे की कड़ी. Okay, English word again. So latch has come because it will latch the output. Okay, it will latch the data, whatever has been fed at the input. Okay, it will latch or it will lock. Okay, that's why it is called as SR latch or SR lock. Okay. Fine. So is that okay till now? Fine. Now see, still there are some undesired situations here. What are the undesired situations? This is when when the enable is 1, still they are changing, right? So when is this thing happening? You tell. See when is this thing happening here? जब ये QA और QB equal रहते हैं ना, तभी ये situation होती है. Okay. So the best thing to avoid this situation is to always make sure that these two inputs are not always equal. Okay, make sure that the inputs to this latch is not always equal. They will always be a complement of that. So what should I do? I'll simply apply a NOT gate at the inputs of this terminals, right? So can you draw the circuit? Draw the circuit. So NAND based. What I'm saying is, so this NAND gate circuit will remain the same. Draw fresh circuit. Draw it by your own. QAN, QBN, enable. Why this enable pin was there? Yeah, so as to control that whenever we wish to feed the data in, then only it should take the data inside. Otherwise it should it should make the change, it should retain the state, right? See, when enable pin is 0, see the change, there is no change, isn't it? I mean, if not equal to, we'll come to that. We have avoided that situation by this one. Okay, we have avoided that situation by introducing this one. Let there be, now there will be only one input. Okay, there will be only one input. See here. Can you prepare a characteristic table for this? Quick. So this, I'm naming it as D, and the output there, this, there's a one input, and this, sorry, there's an enable pin also there. There's an enable pin also there. So write it here. There's a enable pin also there, right? So this is enable. Now you need to take two cases. When enable is 0, you tell me, let's prepare the characteristic table for this. Only two inputs are there to enable, and there's a D here. Output QA and QB, and enable pin, let it be 0. What happens when it is 0? See, both of this NAND gate, now when it is 0, when both of the input is, one of the input is always 0, what is the situation? Output is NAND gate. A NAND gate, output is always 1, right? So output is always 1 here. 1. What is the thing which is happening when it is 1? The previous state will be maintained if it is, that if both of them are different, and so on. Let's consider case. Now that means what? When 0, let's consider this case afterwards. Let's consider the case afterwards. Let it be, let the enable pin be 1. Let the enable pin be 1. Enable, let it be 1. What happens when 1 is there? Then D has two cases. It may be 0 or it may be 1. Let it be 0 first. D 0 है यहाँ पे. यहाँ पे क्या आएगा? 1. You tell me. I mean, 1 1. The output of this will be 0 here. What is the case here? 1 1 0. Now it is as good as the SR latch, like 0 1. This will always be 0. QA will be always 0. 0 1. Is that okay? Is that okay? So this is stable situation. No further change. Assume the other case, when D is 1, what happens? 1 0. Is that the case? Stable 1, stable situation, right? Assume that the output may be 1 or 0, okay, and I press enable equal to 0. What happens? Now the outputs are different, right? So what I'm saying is, जल्दी बता दिया मैं कह रहा हूँ कि enable pin जो है पहले 1 था. Now there are previous state. Now assume that this is a data which we need to feed. Let it be 1. Data input, let it be 1. And enable pin is something like, when we want the data to be inserted or to be saved, we enable that pin. That means we make it 1. Assume that both are 1 1. What happens? That means this situation, right? ये दो वाला situation. The states will be 1 0. Let me write that 1 0, right? And let me suddenly push enable equal to 0. I simply remove that. Okay, I don't want any data to be inserted now. What happens? This 1 0 will be retained. Just because for 0, now the situation is, see here, enable pin is 0, right? So enable is 0 here. Let me write that 0 0. What is the 0 0 for this? What is the output? 1 1. What is the case for 1 1? They will be retained. When they are different, it will be retained. Our purpose is done. Okay, what was our purpose? Our purpose was to come up with a memory element wherein we can give some data that will be retained. Once data goes on, it will be retained when the enable is it is disabled. Okay, whenever it enabled, okay, data will take data will be inserted, and whenever we close that switch, it will be retained. Is that okay? Now this is called as a D latch. Okay, as a D latch. Now यहाँ पे हो क्या रहा है? मतलब इनपुट जो है वही आउटपुट में आ रहा है ना. इसका फायदा क्या है? फायदा ये है कि वो सेव हो रहा है. That is called as a D latch. It's called as a D latch or a delay latch or a data latch. Is that okay? Yes, please. Last वाला. Okay, last वाला. मैंने अभी ये कंसिडर किया है कि see usually that is how the things is happen. That is how the thing happens. मतलब क्या? ये मेरे पास बक्सा है. उसमें मैंने डेटा दिया है 0 या फिर 1. Okay. When it will be enabled only when the enable pin is 1. Assume this case. Okay. Which case? When the enable pin is 1, data may be 0 or 1. You assume any case. I have considered data as 1. What happens when it is 1? That ये सब रब करना पड़ेगा मुझे. Yeah, so when data is 1, right? Data is always 1. Enable pin क्या है? Oh sorry, data is यहाँ पे 1 है. Data is 1 here. यहाँ पे 1 है ना? यहाँ पे इसका complement होगा 0. Enable pin always 1 है. यहाँ पे situation output बोलो 1 1 का. यहाँ पे क्या आएगा? 1 0 का. This is this is okay. Now this is as good as SR latch which we have seen previously. What was that? S ये था ना, नीचे वाला S था ना, मतलब यहाँ पे output 1 आना चाहिए. यहाँ पे 1 लिखो, यहाँ पे 0 लिखो. Is that a stable output? Yes, that means data जब 1 था, output में 1 और उसका complement available है. Now that's why remember in last class I have written a bar there to avoid confusion. Now that is not always the case, but here that will be the case when you enable the thing. Okay. Now you take the situation when it is 0, same thing would happen and you would retain 0. Now once the data has been inserted, you remove that. I mean you disable the enable pin. The data will be latch or lock. Okay. As long as you retain the power. Now see here. Note my words. I am saying that the data will be retained as long as the power is available. Okay. Fine. So this kind of is called as a D latch. Okay, data latch or delay latch. Now, sorry, I should complete this table. What happens here? Doesn't matter what the data is. No, it will be no change, right? No change. Is that okay? Now, okay. So let me name this. Okay. So this is a latch. Okay. So this is again an interview question. Latch. No, many people have written. I think see. You may be already aware of the things कुछ लोग हैं जिनको digital electronics पहले से बताया, but there, as I said, there are some subtle gaps, okay, which are always there. Okay, I'm trying to fill those gaps. Many people may assume this as a D flip flop. Okay, that is what I will come to that later. but this is not a flip-flop. Okay, let me tell you, this is a latch. Interview question is, what is the difference between a latch and a flip-flop? It's always, best interview question which has been, widely asked interview question. So a latch is just because it's a, it's a the things, the memory element which is sensitive to the levels. Okay, levels in the sense sensitive to the levels of the enable pin. ये data तभी this latch is getting enabled only if the enable pin is 1 and the level is 1, always the 1. I mean, it should always be constant. This is level sensitive, you can say, a memory element. Okay, level sensitive memory element. So let me write that. So it's a level sensitive फेवरेट इंटरव्यू क्वेश्चंस ऑलमोस्ट सब लोग पूछते हैं. मेरे को खुद को पूछा गया था बीटेक में, तब मेरे को पता नहीं था, तो कुछ तो जवाब देके हो गया था मेरा. तो यू शुड बी वेरी कॉन्फिडेंट जस्ट बिकॉज वी आर नॉट ट्रीटेड द सेम दैट यू हैव बीन ट्रीटिंग. ओके, सो लेट्स स्टॉप हियर फॉर टुडे.